Today, in this episode, we are going to use this return ratio analysis technique to find out the output impedance of a linear circuit. We will still use the example of the episode 006, which is the example A14 of the Professor Razavi's book. As you can see in this figure, we want to know the output impedance of this circuit. To calculate the output impedance, we apply a test current, In, and observe the voltage across this test current, Vn. The ratio of Vn over In will be the output impedance of this circuit. This is interesting to know. Calculating port impedance is just another kind of transfer function calculation. Just in this time, the input and the output are both at the same port. So, if we want to calculate the transfer function of this output impedance, we can use the return ratio analysis. The first step, setting the input to 0 and calculate the return ratio. If you set the input source to 0, you'll find this circuit become exactly the same as the one in the episode 006. The next step is to calculate the infinite gain A infinite. Just like the calculation in the episode 006, we set feedback amplifier gain as infinite. This means the differential input of the amplifier will be virtually shorted and there will be no current flowing through the resistor Rm. It's interesting to know, if there's no current flowing through the resistor Rm, then the current flowing into the load will be equivalent to the test current. And the current flowing through or out of the MOSFET will form a closed-loop current that has no portion of In. Since the current flowing through the load VL is IL, and IL equals to In, Vin over In will be Vin over IL, which means A infinite will be VL. The next step is to calculate the factor D. To calculate D, we set the gain of the feedback amplifier to 0, which makes the current flowing through the MOSFET also 0. The voltage across Vin become In times VL in parallel with RR plus Rn. In this way, we'll have the D factor. Now, we have the return ratio, A infinite, and the D. We can use this to calculate the closed-loop gain. The closed-loop gain will be A infinite times R over 1 plus R plus D over 1 plus D. The result is shown here. By observation, we can rewrite this as ZL in parallel with the impedance, and this is the output impedance without loading the L. Okay, now, how about we change the output test signal source to a voltage source? If we use the voltage source as the test source, then the return ratio of the circuit will be different from the one we used above. It is because if you make the input source to voltage, then when setting the input source to 0, we'll have the short circuit at the output. Then the circuit is different from the episode 006 and the one we just calculated. But we can still use this to calculate the return ratio. Just in this time, the return ratio is different. And it is simple to calculate the return ratio by applying a voltage source. We can simply disconnect the feedback loop from the current source of M and apply a test current. And the return current over test current is the return ratio. Similarly, since we got the return ratio R, the next step is to calculate N infinite. By setting the feedback amplifier gain to infinite, it also makes the current flows through the resistor Rm 0. And since the current flowing through Rm is 0, there won't be a current flowing through Vin and ZL. That's why we have 0 value of the N infinite gain. The next step is to calculate D. We set the feedback amplifier gain as 0. This gives us a result of D factor as 1 over Ro plus Rm. The next step is to use return ratio and infinite D to calculate the closed loop gain. And we will have Zout. It is interesting to know whether you use a voltage source or a current source to calculate the pole impedance. The output impedance are all the same.